Hello everyone. In this video, we are going to write down the structure of the molecule based on the IUPAC name given. From a competitive exam point of view, such an exercise should be useful because in a multiple choice question, they can either give a structure 4 different names or they can give a name and 4 different structures. So therefore, practicing this name to structure should be a useful exercise from an exam point of view. So let's begin. We have our root word is undecane. So that means in principle we should have 11 carbon atoms, but we will see whether it has 11 carbon atoms or not. Okay, so that's our parent chain. And 5.5, what does that mean? 5.5 means in a Spiro case, it just means that we have 2 6-membered rings. So let's draw the 6-membered rings first, and later on if any change is required, we will do. Okay, so that's a 1 6-membered ring. So that's another 6-membered ring. So that's our Spiro center. And now we have tetraoxa, 2, 4, 8, 10 tetraoxa. So that just simply means that we have oxygen atoms inside the part of the parent chain. We have 4 oxygen atoms which is part of the parent chain. Okay, so therefore that means that not all of them are not carbon atoms. Okay, so we begin the numbering one step away from the spirocarbon. So this is, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now what it says 2, 4, 8, 10. So we have 4 oxygen atoms. So let's make the change at 2 and 4 and then 8 and then 10. So let's put the oxygen atom here, here, here as well as here. Now it also says 3,9 dimethoxy. So one methoxy group here, another methoxy group. Okay, so that should be the structure of the molecule. Let's move on to next example. We have a bicyclic compound here, a fused one, not a bridged one, and the reason we say so is because the value of Z is 0. So it's a fused bicyclic compound. Okay, and we also have magnesia, so dimagnesia, that means 2 magnesium atoms are there, and then act is our root word. So that means total 8 atoms in the parent chain, and we do have a alkene. So let's draw the structure. So 3, this 3 and this 3, so basically 3 plus 2, 2 bridgeheads, that means we have a 5-membered ring, and here also plus 2 for the bridgeheads, we have a 2 5-membered rings. So let's draw the 5-membered ring first. And now, as you know, numbering starts from the bridgehead position. So this is 1, this is 2, and then this is 3, 4, 5, 6, 7, and then 8. Now at 3 and 7 we have magnesium atoms. So let's put the magnesium atom there at 3 and 7. Mg, Mg. Okay, and then between 1 and 5 we have a double bond. So which is here. Okay, that completes our structure for this name. Okay, let's move on to the next example. Now once again we have a bicyclic structure, but this time we have a bridged case because the value of z is 1. Okay, so let's first write down the basic skeleton first. So 2 plus 2, which means a 4-membered ring. Here also plus 2, 4-membered ring, and then 1 plus 2, so that's a 3-membered ring. So the structure is gonna be like this. The basic skeleton. Okay, numbering starts from here, and then at 2 position we have an alkene, and then at 2 position we also have a carboxylic acid. So let's write that 1, 2, 3, 4, 5, 6, and then at 7 position we have a lithium atom, and that's why that lithio comes. So is that the correct structure? Yes, we have everything, we have put everything. We have put the lithium atom. Okay, we drew the bicyclic ring correctly. Okay, and then in total we have 7 atoms in the parent chain, hept, 2 ene, 2 carboxylic acid. So this is the correct structure for this name. Let's move on to next example. Our next example is a bicyclic molecule, and we have 2-methylidene as a substituent. What methylidene means is that you have a CH2 group with a double bond attached at a particular position. That's what methylidene means. Okay, and we have an iodine as the functional group. So that means we have a carbene. Okay, and then we do have an alkene between 1 and 3. Okay, so let's write down the basic skeleton first. So plus 2 means that we have a 3-membered ring. Here also plus 2, that means we have a 3-membered ring again, and then the value of z is 0, that means we have a fused bicyclic ring. So 2 3-membered rings fused together. So let's write down the basic structure. Okay, do the numbering. So that's our bridgehead position, 1, 2, 3 and 4. Okay, so basic structure is done, and now at 2 position we have a methylidene. So let's write that. So we have our methylidene, and then in between 1 and 3 there is a double bond. So that is also done, and then at 4 position iodine. So put a lone pair for the carbene. Okay, that's the structure for this IUPAC name. Let's move on to the next one. We have a trispiro compound with sulfonic acid as a substituent and carboxylic acid as the functional group. So keep it in mind that carboxylic acid gets the top priority, okay, compared to the sulfonic acid. So this is still the top priority, that's why this is considered, the sulfonic acid is considered as a substituent in this case. Okay, so let's work on the structure. Trispiro means we have 3 spiro centers. So 2 plus 1 means that we have a 3-membered ring. So let's first write down the 3-membered ring first. So 1, 2, 3, and then this 0 means is that the spiro center is connected to another spiro center. So that is 4, and then we have one more spiro center connected to another spiro center, okay, that is 5, and then at 5 position we have a 3-membered ring again. So let's write that. That's what the 2 means, 6 and 7, and then 1 which is ending at 4. So ending at 4, that's what that superscript 1 superscript 4 means, this one, yeah. So this is 8, and then we have another final one more carbon which is ending at 3. So that means this one, okay. So total we have 9 carbon atoms. So we got the nonane covered, and then at one position put the carboxylic acid, C double bond O, OH, and then at 6th position put the sulfonic acid, okay, we got that. So that's the correct structure for this name, okay. Let's move on to the next one. Now here we have a trispiro compound, okay. So what is this in a trispiro compound? What is this 2 means? As usual we have a 3-membered ring, okay, that's our spiro center. So 1, 2, 3, then 0 means it is directly attached to another spiro center, so 4, and then we have 2 again, so 5, 6, okay, then again 0, that means we have another spiro center that is at 7, okay, and then again we have 2, so 1 3-membered ring, 8 and 9, and again 0. So this again 0 means the only way we can connect is 7 and 3. So that completes our structure. So basically x1 is 2, x2 is 0, okay, x3 is 2, y1 is 0, y2 is 2, and y3 is 0. Do we have the spiro centers at 4, 7 and 3 position? Yes, we do. So we got that, and total 9 atoms are there, okay, 9 carbon atoms are there, total, not 9 atoms in total, but 9 carbon atoms. So 9 carbon atoms are there, so nonane, that also we got, okay. So that should be the correct structure for this name. Let's move on to next example. Now we have a bicyclic compound. So in a bicyclic compound, the very first thing you should do is figure out the ring size. So here you add +2, so that means you have a 6-membered ring, then again add +2, that means you have a 3-membered ring, and then 0 here means that we have a fused bicyclic compound. The reason we add +2 is because we ignore the bridgehead positions while we enter the numbers in the square bracket. So write down the 6-membered ring first, okay, it's a fused one, so write the 3-membered ring, okay, you got that. So write down the numbers 1, 2, 3, 4, 5, 6, 7, total 7 carbon atoms, so that covers the hept. And now we have 1, 2, 4, 5 tetraene. So between 1 and 2 we have a double bond. Between 2 and 3 also we have a double bond. That's why it is 1, 2. Again 4, 5. So that means that between 4 and 5 we have a double bond, and between 5 and 6 also we have a double bond. Otherwise it would have been mentioned as simply 4, okay? But this 4 and 5 continuously means that both at 4 position as well as at 5 position we have double bonds, okay? That covers the tetraene part. And then 7, iletine means we have a carbene. So let's put a lone pair. So that covers the iletine part. So we got the structure for this. Let's move on to next example. So once again we have a bicyclic compound 410. So that means we have a 6-membered ring and a 3-membered ring fused, because the value of Z is also 0 once again. We have an iletine again. So let's put that. Okay, so do the numbering 1, 2, 3, 4, 5, 6, 7. Okay, and now the double bond is between 1 and 6. So let's do that. And then at 2 position again we have a double bond. Okay, and then at 4 position we have a triple bond. Let's do that. So that should be the correct structure for this name. Now you might be thinking that why we are not numbering the other way around, like why we are not giving low number to the alkyne and why we are giving low number to the alkene. Because as per the preferred IUPAC name, you have to give low number to the double bond, not to the triple bond. When a choice exists, you have to give low numbers to the double bond. So here we are basically giving low numbers to the double bond. If you follow the numbering that is in white, you can clearly see that we have double bonds at position 1 and position 2. Position 1 in bracket 6 completes the first double bond. Position 2 completes the second double bond. But if we go on the other way around, then what will happen is you will have the usual 1 in bracket 6 double bonds, and then your second double bond will be at 4. Okay, so this will become like, if you follow the red, this will become like this, and then here you will have 2 ion. That's not correct. Okay, because we are giving low, we have to give low numbers to the double bond, not the triple bond. Okay, so therefore this the numbers that are shown in the white is the correct way. Okay, so this structure is correct. So let's move on to next example. We have a dispiro molecule and our secondary suffix is thialdehyde, which means we have a functional group like this. Instead of aldehyde, if it is aldehyde, C double bond OH, but now we have a thialdehyde. Okay, so let's write down the structure. So this 2 plus 1 means we have a 3-membered ring first. So let's write down the 3-membered ring. So 1, 2, 3. And then this 0 basically means that 2 spirocarbons are directly attached. Okay, so that's 4. And then these two basically means that again we have a 3-membered ring which is at 4 positions. So that's why superscript 4. Okay. So basically our x1 value is 2, x2 value is 0, because both are, one spirocarbon is connected to the other spirocarbon, that's why it is 0. y1 value is 2, okay, that is this one, and then y2 value is 2. Now y2, where it starts? Shall we start at 5? No. Shall we start at 6? No, because the superscript says that it is connected to 3. So we have to start at 4 and end at 3. Okay. You should not think that, okay, this is, this is a 3-membered ring plus 1. This is a 3-membered ring. How about the last one? It should also be a 3-membered ring. No. This is a 4-membered ring because we are starting at one spirocarbon, ending at another spirocarbon. So, but basically we have 2 carbons. That's what we are counting here, okay, for the y2 value. Okay, so it is not a 3-membered ring, it's a 4-membered ring, but 2 spirocarbon positions are ignored. That's why we are entering 2. So this is 7, this is 8. Okay, so we got the arct correctly. And now at 7 we have ene. So put a double bond there. And then at 7 position again thialdehyde. Put the functional group there. So that completes the structure. Our next example is a tetraspiro compound, and we have our root word hexadecane, that means 16 carbon atoms in the parent chain, and tetravone, that means 4 keto groups are there. Okay, so let's work it out the structure. So as usual, the first 2 means that we have a 3-membered ring. So let's draw the 3-membered ring first. Let's number it 1, 2, 3, and then 1 means that there is a 1 carbon between this one, this spirocarbon 3 and the next one. So 4, let's call this as 5. Okay, and then at 5 position we have another 3-membered ring. So let's draw a 3-membered ring again, number it 6 and 7, and then again 1. So 1 carbon, this is 8. Sorry, let's number it inside so that, yeah, so this is 8, this is 9, okay, and then at 9 again we have a 3-membered ring, this one, okay. So 10, 11, again 1, that means 1 carbon. So 9, 10, 11, 12, this is 13, this is 12, okay, and at 13 again we have a 3-membered ring. So let's draw that. Okay, 14, 15, and then again 1, and that again 1 is connected to 3. So that means we have to end here. Okay, so connected to 3, starting from 13 and ending at 3. So this is 16. Now, where the keto groups are? The keto groups are at 4, 8, 12, 16. So let's draw the keto groups there. So this is 4. So at 4, 1 keto group, 8, 1 keto group, 12, 1 keto group, 16, the last keto group. So 4 keto groups we have put. So that's the correct structure for this tetraspiro molecule. Let's move on to the last example. Our last example is a pentaspiro compound. I know I haven't made separate videos for pentaspiro compounds, but based on our experience or whatever we have learned so far, we would be able to draw the structure for this easily. So let's do that. Our root word is pentadecane. That means 15 carbon atoms in total. Okay. So let's start. 2 means we have a 3-membered ring. So let's draw the 3-membered ring first. 1, 2, 3, and 0 means one spirocarbon connected to another spirocarbon. So let's call this as 4, and then at 4 again we have a 3-membered ring. 5, 6, again 0, 7, and then at 7 again we have 3-membered ring. Let's draw that. So this is 8 and 9, again 0, one spirocarbon connected to another spirocarbon. So 8, 9, so this is 10. Okay, and at 10 again we have 3-membered ring. Okay, 11, 12, again 0. So that is 13, one spirocarbon connected to another spirocarbon. At 13 again we have a 3-membered ring. 14, 15, and finally this 0 connects to 3. So that means we have to draw a bond between 13 and 3. Both are spirocarbons. So that's the structure for this name. Do we have 15 carbon atoms in total? Yes, we do. Okay, so this is the pentaspiro compound, pentaspiro pentadecane. Okay, so if you do like this video, consider subscribing it to Chem Media, and thank you for watching this video.